Okay, I guess we can go ahead and get started. Maybe a few people will trickle in. Okay, so we've talked in the last few lectures about expander graphs and their applications in coding theory. And we've also actually seen a little bit, Swastik mentioned sort of the failure of expander graphs in these code constructions where you can't get local testability automatically. And I won't go through a bunch of examples, but they're, along with sort of the huge success of expander graphs in computation and understanding mixing of random walks, like Dinur talked about, and in coding theory, there are many settings where expanders don't seem to capture the full structure of a problem, like in local testability, or we'll see some examples in sort of sampling high-dimensional distributions. Often, a reason for this is that a lot of problems we like to study in computer science are high-dimensional in some sense, right? If you have data, you have a vector with many different features, or you care about optimization over many variables. In a lot of cases, these are sort of inherently high-dimensional problems, and while you can make some progress by using graphs and expanders to look at them, often you can't get all the way to sort of the optimal solution you're looking for. So in the past 10 to 15 years, there's been a pretty concerted effort in the community to push the success of expander graphs from, depending on how you look at it, either 1 or 2 dimensions to higher dimensional objects that will sort of fix this gap that we see for these problems. And we'll discuss explicitly some examples over the next 3 or 4 lectures on high dimensional expanders where these gaps actually got resolved using this theory. Okay. Actually, maybe I will just list like some problems where moving to high dimensions ended up being very successful. So mixing of high dimensional random walks. So we'll mostly see the resolution of what's called the Mihail-Vazirani conjecture, which has to do with actually the edge expansion, but we'll look at the spectral expansion of a certain walk on matroids. We'll mostly focus on spanning trees, but we'll actually see this explicitly. It was open for 30 or so years to analyze sort of the spectral gap of this high-dimensional object we'll talk about. And there's a really, really beautiful and elegant resolution of this through the theory of high-dimensional expansion that we'll prove. Other things we'll see some connections to solving CSPs and list decoding. Maybe Dinur will talk about these several lectures down the line. Things that we won't get to, but we'll develop some techniques that were really crucial in developing these results are the new quasi-linear PCPs. Obviously, there's the locally testable codes that have been mentioned, although I'll mostly be covering spectral stuff, whereas the locally testable codes will be largely topological stuff, and we'll talk about that later as well, but the C3 LTCs. Okay, anyway, over the past 5 or 6 years, we've seen a huge amount of progress coming from these objects. And so hopefully you're convinced they're worth understanding. So with that, let's actually get into some of the technical content. What are high-dimensional expanders? Why are they defined the way they're defined? And how do we do analysis and computation using them? Okay, I sort of lied. I guess some of you can't see pi that's written here. But we actually need to go back to low-dimensional expanders for a little bit, because we need to do sort of one more generalization on top of what Dinur did in the previous lectures. So we'll sort of go back to graphs. And this time, so Dinur started with regular graphs, talked about the normalized adjacency matrix, its spectrum, and spectral expansion. And then he talked about how to extend this to irregular graphs, right, by doing a weighted, the weighted adjacency matrix sort of corresponding to the random walk on the graph, and then how this was self-adjoint over the correctly normalized inner product. Now we need to generalize to general weighted graphs. So instead of, we won't care anymore about regularity or irregularity, our graph will come with a distribution over edges, and we'll use that distribution to define the random walk and adjacency operator and spectral expansion. And this will end up being important in high-dimensional expanders because the distributions end up not being uniform, a way that we'll talk about later. Okay, so definition, weighted graph over, so I'm just always going to have a vertex set being n, numbers 1 through n for simplicity in this. So over vertex set n is just a pair. E pi 2, where E is what you think it is, right? E is just the edges, the subset of pairs, and choose 2. And pi 2 is just a distribution over E, right? So it's some positive weights that sum to 1. Okay, so the first question that arises is how do we define the adjacency matrix corresponding to these weights in a natural way? Yeah. In this definition, you do not include self-loops because these are unordered pairs. Everything we're doing will generalize to the case of doing self-loops, so I'm sort of just going to ignore this. But yeah, it's a good question. Okay, so how should we define the weighted adjacency matrix and normalize center product in such a way that we get something that's self-adjoint, we get a spectral decomposition, et cetera, and can generalize expansion? I claim that, and there are many ways to do this, I claim that one natural way to do it is to look at what the underlying random walk corresponding to these weights are on the graph, and to just define the adjacency matrix to be the transition matrix of this random walk, right? So let's say we have some graph. I don't know, I won't draw that much of it, but I don't know, we have some graph. And the edges are given weights, right? So maybe this is 0.05, this is 0.15, this is 0.2. How much do I have? This is 0.1. So the sum over the total weights will be 1, right? So if let's say that I am starting at this vertex in the graph, and I want to perform the random walk, and I want to do it sort of with respect to these edge weights. What's the natural thing to do? With what probability should I go from V to a vertex W? Good, yeah, so I just normalized by the total weight around V. That's sort of the only natural thing that we would do. In this case, I tried to make it so that they summed up to 0.5. I hope I did that. I did. So the weight around V is a half. Right, so that just means I'm going to go to W with probability 0.1, here to with probability 0.3, 0.4. 0.2, that's right. Okay, simple enough, right? So this leads to the following definition of the adjacency matrix, which is just probability, the VW entry is just the probability of going from V to W. So the weighted adjacency matrix. I think Madura used bar for this. I will sort of only ever talk about the weighted adjacency matrix, so I'm just going to write A, and it will always be this weighted, this weighted matrix. So this is sort of this probability from going to V to W in this walk. And this is just like we said, it's going to be, well, it's 0 if W is not a neighbor of V. So maybe 0 if VW is not in E. And otherwise, it's this normalized edge weight. So, right, otherwise, it's pi 2 of VW normalized by the sum over all the neighbors of V. So U that is a neighbor of V of pi 2 VU. Okay, that's nothing more than just formally written out what we said over there. Okay. So now I just want to argue briefly. Actually, let's see one thing before moving on. First, I claim that this is exactly actually the generalization that Madura gave yesterday, day before, yesterday for this irregular case where the weights are uniform, right? Because then what does that mean? Each of these weights in the uniform case is 1 over the total number of edges, right? So this will be 1 over E, and there are going to be degree V neighbors. So this is degree of V over E. And so their division is just 1 over degree, which is exactly the normalizing factor that we had before, right? So this generalizes this irregular case that Dinur did before. And the reason why this is self-adjoint, et cetera, and the right inner product are all similarly going to be basically exactly generalizations of this irregular case that we did yesterday. But I'll do it a little bit carefully just to make sure that everybody's on the same page, and because we're going to see it come up again with numbers above 2 in a few minutes. So let's make sure that we get the D equals 2 case pretty much down. Okay, so now I want to define the right inner product over which A is self-adjoint. And the way that I'm going to do this, like we did before, is define sort of the right weighted distribution over vertices. To define the marginal distribution of pi2 over vertices. So the vertex marginal, is this too high? No, this should be fine, right? So we'll denote this as pi1. Right? Pi2 is the edges, pi1 is the vertex distribution. And I mean, there are a couple ways to think of this. Pi1 could be just sort of the stationary distribution if you're connected. But we'll think of generating pi1 through a simple process. We'll draw an edge from pi2, and then I'll just randomly pick one of the vertices, a random endpoint of the edge, right? So it's pi1 is generated by the following process. 1 sample VW from pi2, and 2 just pick V or W each with independently with probability 1/2. So choose V or W independently. Okay. So now we can define a normalized inner product over pi1 like we did before, right? If we have functions f and g. Sorry, that's HDX notation. On the vertices of this graph to the reals, we get this inner product, which is we write as fg. Technically, like this is over pi1, but we're always going to be sort of over these well-defined marginal distributions. So it should basically always be clear what the inner product is. This is just the expectation over v drawn from pi1 of f of v times g of v. Okay, and the claim is that A is self-adjoint with respect to this inner product. In particular, we claim that like f A of g is just the expectation of f times g across an edge in the graph. That this is expectation over an edge. And I think Dinur went through basically exactly this calculation for the other cases. Is this area seeable for people, or I should avoid? So, okay. Okay. Well, the point is that this is, both of these are just the expectation over an edge. It doesn't matter which side we apply A on. And I actually want to take a moment to argue, maybe not formally why this is true, but at least morally why this is true, because this sort of argument is going to come up again and again when we move to higher dimensions. It's not complicated. The point is just to notice the following, or maybe I'll say, let's sort of recall, what is the action of A on G? A averages over the neighbors. What is AG of V? This is just the average value of G across all the neighbors of V. But of course, this average is taken with respect to this pi2 distribution, right? This is sort of the local, the the local conditional distribution around V, right? So I should really think of this probability here. I'm going to write it as pi upper V of 1 as being the conditional distribution over vertices conditioned on already having picked V. Okay, why am I going through this? So this is equal to the expectation over W drawn from this conditional distribution on V of G of W. Okay, why did I make such a point of this? Because now I claim this is going to be very obvious. Once we've started viewing A as the expectation around the conditional distribution on V. And in particular, we have like f of AG is what? So let's write this out. This is the expectation over a vertex drawn randomly from this pi1 vertex marginal distribution of f of V times now the expectation of W drawn given V, right? First I draw V, then I look at, we had this graph picture before. First I've drawn V, then conditioned on V, I've drawn my edge, VW. Right, so this is now the expectation over sort of the neighborhood of V, or this conditional distribution of GW. But the point is that, I can shift this expectation outside of here. Right? So this is just the process. This is the expectation over pairs, V drawn from pi1 and W drawn sort of conditionally from V. I'll just write it as W tilde V of f of V G of W. But drawing V from the marginal and then W conditioned on V is the same as just drawing an edge, right? In this graph, I've just drawn a completely random vertex and then a random neighbor appropriately weighted with respect to the distribution. That's just a random edge. And I could have done this the other way too, right? I could have drawn, W and then V, and this would give me sort of the flip AFG. Both of these are just the expectation over a random edge of the graph. Okay, I've belabored this maybe a little bit too much, but this view of sort of this local distribution as being the conditional distribution on V is very, very useful when you start moving to high dimensions. We're going to start having to work with sort of higher dimensional conditional distributions, and it's useful to be comfortable with this sort of manipulation. Yeah.
A times G of V, independent of V?
Oh no. This is the expectation is over the local neighborhood of V. Right. So this is drawn from this distribution, which is dependent on V, right? This is the distribution is exactly, it's only supported on the neighbors of V, and it's distributed by pi2. Right? So it's the marginal distribution conditioned on V. So it's very much dependent on V. Yeah, thanks. Sorry, this was maybe a little small. How is pi through this process, right? I sample a random edge, and then I randomly pick one of the vertices in the edge. So in this sense, it's like the one-dimensional marginal of this distribution. Sorry? Oh, the conditional distribution. I mean, the conditional distribution is exactly this. Yeah, actually, let's make this more explicit. So I can actually write this in terms of pi1v, right? This bottom denominator, what is this? This is the sum. This was this normalizing probability, right? It's the, I'm not supposed to write. Oh no, I can write here. Right, it was the sum, if this is V, it was the sum over all these edge weights, right? Yada, yada. But I claim that this is like exactly half of pi1v, right? So this is equal to half pi1 of V. Why? How's pi1 defined? Sample a random edge, subsample a vertex randomly. So how's the only way I can get V, right? First, I have to sample an edge that contains V, and then there's exactly a half probability that I then randomly pick V from that edge. So this total sum, this total sum is twice the probability of sampling V, because it's the total sum over things, and then it would be half that I pick V. So then maybe it should be more clear that this is the conditional distribution, right? Because this is just pi2 of VW up to a normalizing factor 2 of moving between edges and vertices, divided by the probability of being around V. Okay, sorry, that was a little bit more detail than I had planned to go into, but is that reasonably clear? I'm going to show maybe a slightly more clear version of this for bipartite graphs, where things are sort of more obviously conditional distributions than in the set case, which has sort of these weird normalizing factors that are a little bit annoying. But, okay, anyway, let's move on, since this is a little bit in the weeds at this point. So now that this is self-adjoint, it has a spectral decomposition, et cetera, and we can define expansion as we did before, right? So I'll just write it to remind us that G is called, G is a lambda one-sided spectral expander. If lambda 2, if the second eigenvalue of this normalized adjacency matrix, right, these are still, just like last time, right, these are still n eigenvalues. This should be equals between -1 and 1, and our expansion will either be lambda 2 or the maximum of lambda 2 and the absolute value of lambda n. So that's the two-sided. Lambda is less than or equal to maximum. Sorry. Maximum of lambda 2. Lambda n is less than or equal to lambda. Okay. So we have our full definition of spectral expansion for weighted graphs. Okay. There's one more thing I want to talk about before moving to high dimensions and defining, moving to hypergraphs and talking about what the natural definition of spectral expansion there is. And it actually does relate to sort of this conditional probability stuff that we were doing here. And in fact, it's a much easier version of it, which is why I was planning to ignore this initially. I'll erase this, I think. I want to talk a little bit about viewing graphs and expansion in sort of a distributional sense, as a property of distributions or random variables. And we're going to see that this notion extends really nicely to high dimensions. Okay. So we can always view a graph basically as a two-dimensional random variable coming from picking a random edge from the graph. So say you can view a graph G basically just as a distribution, a random variable, x1, x2, where the value of this variable is coming from sampling a random edge in the graph. This is supported on and choose 2. And in essence, when we were taking expectations and looking at these distributions over here, we were already really doing this implicitly. We were already working with this random variable that was just corresponding to picking a random edge from our weighted distribution. So we've already been doing this. There's nothing really new here. This becomes much cleaner in the bipartite case, right, which Dinur talked about a little bit, right? For bipartite graphs, we have two sides. And in this case, instead of these edges being a set, we can actually think of it as sort of a true two-dimensional random variable or distribution, right? That we can think of, I'll make this. We can think of a variable sort of x1, x2, where I draw a random edge and x1 takes the value of the left vertex and x2 takes the value of the right vertex, right? So if this were like 3 and this were the first vertex, then this would be taking the value 3, 1. Okay, so it's just a two-dimensional distribution. Yeah. Sorry. Yeah, it's A is only self-adjoint with respect to this new inner product, right? So it's not even well defined over a standard. So everything will always be weighted over pi1. For all the remaining lectures that I do, at least everything is weighted over these pi distributions. And right now we have pi1, pi2. We'll later have pi3, pi4, pi5, etc. Everything will always be with respect to these distributions. And here also we have this is distributed as pi2. Etc. Okay. What did I want to say? I just wanted to say we can view these graphs as sort of true two-dimensional random variables, right? And this connection also goes both ways. If you just give me a two-dimensional random variable that's supported over some finite, say both of these are supported on n, then this also corresponds to a weighted graph. Right? How do I get the weighted graph? Bipartite graph. I draw n on each side. For every pair that is in the support of this distribution, I draw an edge, and the probability, the weight of that edge, is just the probability that the pair appears in the distribution. Right? So these are totally equivalent ways to think about these objects. And in fact, as we've been doing these, expectations and inner products and analysis, all of them have really been happening over these distributions. We were just sort of hiding it before, but now I want to make it explicit because when we move to high dimensions, it's going to make things easier. Okay, so in this distributional view, what does it mean for this two-dimensional distribution, this graph, to be a spectral expander? Okay, it means that lambda 2, what I view the adjacency matrix is bounded. But there's also a very nice interpretation that Dinur talked about, which was this sort of expander mixing lemma type result. And how can I think about that here? Well, I can sort of rephrase things to basically say that a graph is an expander. Its two-dimensional distribution is an expander if x1 and x2 as variables act independent. What do I mean by this? The expander mixing lemma that Dinur proved essentially says that if I have a function f sitting on the left-hand side and a function g sitting on the vertices on the right-hand side, that the expectation of f times g taken over this joint distribution, right, taken over an edge, is roughly equivalent to just the expectation of f times the expectation of g. Up to plus or minus lambda times the variance of f times the variance of g. So this is actually an equivalent formulation of spectral expansion. One direction Dinur basically showed was the expander mixing lemma. The other direction, I guess maybe I'll leave it as an exercise if you want, but it's just literally the definition of lambda 2 or lambda 2 at lambda n here. So this sort of this fact that the joint expectation over x1, x2 basically splits, like it acts like expectation of f times expectation of g. It's really useful to think of this as sort of these variables are approximately independent in this sense. At least on average, I can just treat them up to this lambda error as if they were completely independent random variables. Yeah. Yeah, thank you. So this is with respect to the joint distribution x1, x2, which, as you said, is distributed like pi2. And this is just with respect to x1, which is the marginal distribution, right? So now that I have x1, x2, when I have this view of things, this is like how is the left part distributed and the right part distributed? I draw a random x1, x2, and then to get the left guy, I would project to the left coordinate. To get the right guy, I would project to the right coordinate instead of picking one at random, which would have been the unordered case, right? So then this gives you sort of a coordinate 1 version of pi1 and coordinate 2 version of pi1 here. So these right expectations are just over the marginal distributions of x1 and x2. And now what I wanted to say in this version is that all this sort of annoying calculation we did about conditional distributions, now it becomes extremely obvious. Right, because this is literally just a two-dimensional random variable. what does it mean, when we had this like inner product AFG before? What we were saying is that this is maybe FAG. This was basically like first I draw the value of x1, and then I draw x2 conditional on the value of x1. That's exactly the same thing. The law of total probability says that's exactly the same thing as just jointly sampling from x1 and x2, right? That's when you sort of view things in this way, the self-adjointness of A becomes trivial. It's just the law of total probability that sampling from x1 and then x2 conditional on x1 is exactly the same as sampling from x2 and then x1 conditional on x2. They're both just an edge from this, right? They're both just the joint distribution. So when things are sets, it's a little bit annoying because you take a random, a random vertex and there's a normalizing factor due to this. But morally, you can really think of everything in this sort of setting where, when we fix a guy V here and we look over its neighbors, this is literally the conditional, distribution of x2 conditioned on x1 being V. That we've defined the adjacency matrix in such a way that this is how the distributions work. Yeah. So you can transfer everything both ways here, right? If I take the 2D random variable and I draw the graph and I define the adjacency matrix in this way, and then I were to transfer back, I would get the same, same x1, x2. They're completely in one-to-one connection with each other. Okay, so in this case, sort of we have this nice, I think, expression of expansion that it's just saying that the variables x1 and x2 act independent. And let me then tie this back to something that Dinur said before. Dinur said we should, one way that he gives several interpretations of this expander mixing. And one way was he was saying that it basically acts like the complete graph. So what does it mean in graph land for x1 and x2 to be independent? It actually means this graph is complete, right? If this is independent, if there's no dependency when I look at the right-hand side on whether I'm V or something else, this means that V has an edge to every possible guy, right? So these two things being independent is exactly saying that this is the complete graph. So this is actually the same interpretation that Dinur was talking about. This says that expanders are, sort of sparse graphs that act like the complete graph, or equivalently, their variables act independent when you look at them in expectation. Okay, right. If there are no more questions, I'll move to high-dimensional expanders. Good, yes. So something would be bounded degree if, like, for every setting of x1, there's only, 5 possible values in the support of x2. Yeah, so the degree is exactly the size of the support under this condition. Good. How am I doing on time? I think I'm way behind. All right. Okay, so now I am hoping to say that now that we have this view that we've spent half an hour developing, that there will be a very natural way to extend this to hypergraphs. Okay, so let's actually move to high-dimensional expansion. Okay, so the goal is basically just to generalize everything we just did over there, but now 2 will become D, where D can be, anything you want above 2. So there are actually a number of different types of high-dimensional objects you could try to generalize graphs to. For my lectures, I'm just going to work with the simplest of these, which are hypergraphs. Later, we'll see, Pavel will talk about chain complexes, and we'll see some other types of generalizations. But for now, uniform hypergraphs. So let me remind people what these are. So a weighted, let's say, D uniform hypergraph. Now you're realizing people use D for degree before, and I'm using it for dimension. So apologies for that. D means dimension for the rest of this. Again, we're just going to work with vertex set n always on n vertices. Is almost exactly what we had in the graph case, but now it's going to be a pair H by D, where H is a subset of d tuples, and pi d is just a distribution over H. Okay. So when d is 2, this is exactly a weighted graph, right? But when d is 3 or higher, then we're working with some higher dimensional structure. Okay, so it turns out that in defining expansion, it will be very useful to work sort of not with the hypergraph, but what's called the simplicial complex corresponding to the hypergraph H, or the pure simplicial complex. This is maybe a scary word, but it literally just means I'm going to downward close this hypergraph H. Just for every hyperedge of size, D uniform meant all my hyperedges were size D, were D tuples. Now for every D tuple, I'm just going to add in all of its subsets. So I've actually just drawn a diagram here that we can directly look at. Here I've started with, I guess, the complete 3 uniform hypergraph on 4 vertices. So I have every triple of 1 through 4 in here, and we create the corresponding simplicial complex just by downward closing it, right? So for 1, 2, 3, we add 1, 2, 1, 3, and 2, 3, which should be somewhere, and 2, 3, etc. Right? It's not a complicated procedure, but let me write a definition. So the simplicial complex X, weighted simplicial complex, maybe I should say X pi, corresponding to H, consists of sort of the union of all of these levels, right? Sets of each size that are induced by downward closure. So this is the union of x0 through xd, where xi is a subset of n choose I. These are the I tuples. And like we just said, there are all I tuples that appear in some D set in the original hypergraph. So it's just a downward closure. So given by downward closure. Okay. And this downward closure operation, it also induces a natural distribution on all of these levels. Right? So we started with a weighted hypergraph, which meant we had some distribution pi 3 in this example up here. And how are we going to generate pi 2, pi 1, etc.? Well, just like we did in the graph case, right? If we have pi 3, we sample an edge by first sampling a random one of these, and then randomly taking an edge out of this 3 tuple. Right? So each pi I, so the corresponding distributions, pi I over xi, and again, like this is what we're going to use to define inner products and things being adjoint. It all naturally generalizes the things we did over in the graph case. Is by the sampling process. So the following process that I just said, we'll sample S, a D tuple from pi D, and then we'll sample uniformly at random. We'll sample a subset T of S, where the size of T is I. Okay, so this gives us a series of distributions over each level, right, of the complex. I guess pi 0 has weight 1 on the empty set. And these should be viewed in the same way that pi 1 was viewed as sort of the marginal distribution over vertices in the graph. Each pi I should be viewed as sort of the I-dimensional marginal of this D-dimensional object, the D-dimensional complex. I guess we could write, very explicitly that pi I of t is equal to 1 over d choose I, sort of normalizing factor of picking a particular I face out of a D face, times the probability of S drawn from pi D that T lies in S. Oh, I wasn't supposed to write beyond here. That T lies in S. Right, this is exactly the same thing, saying, how can I possibly sample T? First, I have to sample something from the top that contains T, and then with probability 1 over d choose I select T randomly. So we can explicitly understand these probabilities. Okay. So now let's actually get to, well, I say the payoff, but the payoff here is really just a definition, which feels a little weak, but eventually we'll get to some theorems using the definition that will be strong. So now we can actually define high-dimensional expansion. So maybe I'll pause. Are there any questions about this definition, the hypergraph or Deborah enclosure? Yeah, Prahladh. Oh, thank you. I did mean to say that. Yeah, there's some discussion of this in the lecture notes that are posted as well. So I am sort of committing a mortal sin here, if you're from the math community, which is that there's a whole other way to view these objects. I call them simplicial complexes, right? And if you're from math, you know that that would really be viewing these as like a set of triangles that are, in particular, this would really be a pyramid, that there are 4 vertices in the pyramid, right? And then this complex has sort of every triangle in this pyramid, every edge that's in the pyramid, and the 4 vertices that are in the pyramid. And in this case, you know, a triangle is a 2-dimensional object. I can draw it on this 2-dimensional board. So often in the math literature, you will see this called x2 instead of x3. On the other hand, when you're viewing things as distributions or random variables, it makes much more sense to use the set size as the dimension or cardinality. So I'm going to be using set size in my notation for these lectures, for which I apologize. But when you try to do combinatorial or probabilistic analysis, it is a nightmare to use the I-1 dimension, and you do not want me to do it on the board. So we'll always be using set size instead of dimension. You will see in the literature, papers will use one of these or the other, and usually will say which one they are using. Thanks. Other comments or questions before we define high-dimensional expansion? Okay, great. Okay, so now we hopefully get to see the payoff from the rather lengthy delve into this distributional view for things. It will make defining high-dimensional expansion very, very clean. Let me just get some more board space quickly. Oh, well, okay, we don't need the title anymore, I guess. Okay, so just like graphs correspond directly to 2-dimensional distributions, like we discussed, hypergraphs correspond to d-dimensional distributions, right? In exactly the natural way. So the distributional view. This hypergraph has a 1-to-1 correspondence with the d-dimensional set that's supported on, and choose D, and it's just taking, you know, how do I generate this variable? I draw a random hyperedge or a random top-level guy from the simplicial complex, and my variable gets that value. Okay, so I want to start again by looking at the partite case, which was sort of cleaner because we had coordinates that we could work with, and things were sort of real distributions and not the sort of unordered set distributions. We'll move back to the general set case, hopefully at the end of the lecture. But for now, let's consider the partite case. I should probably tell you what it means for a hypergraph to be partite. It just means, in the d-dimensional case, that there is a partition of the vertices. So in the bipartite case, we had like L and R, right? So maybe not that surprisingly, in the high-dimensional case, we're going to have D parts. I won't draw them all because I don't know what D is. But we'll have parts, etc. And every d-dimensional face will have one vertex from each part, right? So the d-dimensional faces will look like, let's just do B equals 4 for the moment. So they'll look like, you know, one vertex from each part of this structure. Does that make sense? So this directly generalizes bipartite graphs, right? If I were to just cover up this, you know, the parts P1, P2 here are just a bipartite graph. Okay, so in this case, like before, now we get, let's like a real honest-to-God four-dimensional random variable here, or d-dimensional in the general case, where the variable x, jointly distributed. These are, I draw a random hyperedge, and then xi is just the value of which vertex I drew on part I, just like the bipartite case. So now, when should I call this hypergraph or this distribution a high-dimensional expander? That's sort of the key question. Yeah. I drew 4, but sure. Let's say in general, it goes to PD, and this variable goes to XD. I gave up drawing parts after 4. Yeah, D parts, D dimensions, and this variable is just what you think it is, right? I sample a hyperedge, and the ith guy is the ith coordinate, the value of the ith coordinate. Nothing complicated going on. So, when should we call X a high-dimensional expander? Spectral HDX. Well, morally, if I was calling x1, x2 a spectral expander when these variables acted independent, right? When expectation of f times g was close to expectation of f times expectation of g, then it should be some notion of all the variables x1 through xd acting independent, right? This would sort of be the natural d-dimensional generalization. So we sort of want, x1 through xd to act independent. Sort of the same spectral sense. Okay, it's still not immediately clear what the definition should be here, right? There are a number of ways that you could ask for sort of a d-dimensional random variable to have these variables look independent. So maybe I'll suggest sort of 2 ways, and we'll settle on one of them. I could ask that every sort of pairwise marginal in here acts independent, is a bipartite expander, right? So one thing I could ask is, like, for every marginal distribution, xi, xj. So what does this actually mean on the, as a random variable? Hopefully it's clear what this means, right? I draw the whole thing, and then I project on a coordinate I and coordinate j. This gives me a 2-dimensional distribution or a graph. Over here, I can also look at this combinatorially, right? I have this sort of multipartite structure. What is xi, xj? It's exactly, I just look at part I and part j, and I look at all the edges going between them. Right? This is if I look at those weights, it'll exactly be the weights that are underlying this pair xi, xj. So one suggestion is, well, all of the bipartite graphs, in this multipartite structure, or equivalently, all of these 2-dimensional marginal distributions should be spectral expanders. Each pairwise, this is sort of like a notion of approximate pairwise independence of these variables, right? So xi, xj should be a lambda expander for all pairs ij. All 2-dimensional marginals should be expanding. Okay, that's one definition. You might also think to sort of directly generalize the expander mixing lemma, right? Maybe I have functions f1, f2, f3, f4, right, up through fd, et cetera, on the parts, and I might ask for some sort of high-dimensional expander mixing lemma, right? That maybe what I'm asking for is that the expectation of the product of all of these FIs should be roughly equal to the product of their expectations, right? That would also be a natural generalization of this definition. So this should be roughly equal to the product of the expectations of Fi. And again, like before, this is over the joint distribution x1 through xd, and this is over each individual marginal x1, x2, x3, et cetera. And this will be up to something in the norms of f or something like this. Okay, these are both nice and useful notions of sort of weak independence. But I claim that for our standpoint, they're sort of missing a critical piece of the picture in trying to define a sparse model of this sort of independent variables or product or of the complete hypergraph. And that's the behavior of independent random variables under conditioning or under restriction. So a critical property of independent variables that sort of only really shows up in this sort of view, once we go above 2 dimensions, is that if I fix the value of x1, say that I fix x1 equals a. Let's do it down here. I fix x1 equals a, and then I look at the conditional distribution of x2 through xd, conditioned on x1 being a. What does that mean in the graph case over here? I've fixed the vertex a, and I'm now restricted only to sort of neighbors of a in here, right? I look only at the hyperedges that contain a, and now I look at this new graph just with these hyperedges touching a. If these were truly independent, well, this then actually wouldn't change the distribution at all, but that's a little bit too much to hope for, right? If we want a general hypergraph. But at least this remains independent, right? If I fix any subset of the variables, the conditional distribution over the rest of the variables remains independent. So it turns out when you're working with things like spectral analysis or mixing of random walks, a lot of the time you want to do sort of local analysis. You want to do local conditionings. Yeah. A shouldn't be. So, okay. In this case, like you could think of each of these parts as all being n, but as sort of having a coordinate indicator with them. So maybe formally as a simplicial complex, this would be like the vertex 1a, and then there might be a vertex 2a over here. They wouldn't be, you would never have a vertex repeated in the simplicial complex, but formally on these different parts, these are actually, even if I'm labeled A here and I'm labeled A here, these are different vertices because this is A1 and that's A2. Yeah, actually now your question is making me realize that I forgot to cover a component of this, but maybe I'll finish this definition and I'll go back to that. Thanks. Does that make sense? Okay. Yeah, let's try to get through the definition of HDX before we go to break. Okay, so what I'm claiming these definitions are missing is that it doesn't give me any information about what happens under conditioning or fixing some value of one of the variables. And this turns out to be, as we'll see sort of in these later applications of HDX, a really critical component, that we want the behavior of the complex to remain nice even after I fix some of these variables. So this suggests sort of the following definition. Well, I'll take the pairwise definition for the moment. So X is called, so this isn't quite the typical definition of local spectral expanders, which I'll give in just a second, just sort of the unordered variant of this. X is called a lambda product if, I guess I'll say this, maybe formally this is a definition of Gur-Lifshitz and Liu. But as we'll discuss, it's basically equivalent to standard high-dimensional, spectral high-dimensional expansion. If, for all ij, one, this marginal, or equivalently, right, the bipartite graph between part I and part j is a spectral expander. And two, this remains true under conditioning, right? So if this remains true, even if I fix the value, if I look at any subset of variables S, if I look at any subset of the variables outside of xi and xj, and I fix them to be some value zs that's in the support for the distribution, right? Think of if S was just 1, this would be like fixing x1 to be a, like we did over here, or maybe 1a, technically. Then we want that the conditional distribution of xi, xj is still a lambda expander. Okay, so that's the full definition of a high-dimensional expander. We want essentially all of these pairwise marginals in our complex to be expander graphs, to act independent. And we want this to be true even if we fix the value of some of the other variables. Yeah, Prahladh. Sorry? Yeah, item 2 does imply item 1. Yeah. So yeah, I could have just written, you know, xi xj is a lambda expander under any possible conditioning, including the empty conditioning, which would have been the first one. Yeah. Yeah. Well, okay, we only have a definition of expansion for two-dimensional things, right? So I'm trying to generalize the definition of two. So, but okay, maybe the question is, why didn't I use this like expectation definition and have that under restriction? That would be totally reasonable. It turns out it's basically equivalent. So on the exercises, there's an exercise basically showing that you can derive that definition, like all triples or anything will satisfy a high-dimensional expander mixing lemma. If you have that under all conditionings up to some factors of dimension, it's basically equivalent to having this pairwise notion. Yeah, good question. Sorry, say.
You take 3 bits.
Yeah.
Which is the XOR of the first 2. Finding each other.
Yeah.
That's pairwise independent,
but now when I fix one, it won't behave well, right? Sorry, say. Right, the point is if I fix one, then they become, yeah, then they become correlated. Yeah. I couldn't hear the beginning, sorry. Right, so when I define this, I only want to take values zs that actually appear in the support of xs. Yeah, so technically you could say for all and then say it's either empty or it's a expander. Good question. I'm just assuming that this is in the support of xs. So for any valid possible setting, you know, pinning of these variables, I want the remainder to still act independent, right? Okay, I'm almost out of time. I guess let me do the unordered, the sort of full general version, and then we'll go to break if that's okay. So after, something that I didn't say that I wanted to say is in this translation, in 2 dimensions, I talked about how, you know, any pair of random variables is a graph and any graph is a pair of random variables. The same thing holds true over here, right? Any d-dimensional distribution, I can draw the corresponding weighted hypergraph. And this means that a lot of classical objects in computer science, like the hypercube, for instance, products of Bernoulli random variables, product spaces, lots of things that we have many, you know, nice analysis, nice knowledge of the eigenvalues, eigenvectors, etc., fast mixing. All of these can be expressed as special cases of partite or general simplicial complexes. And a big theme that we're going to see going forward is that we can generalize a lot of these classical tools in theoretical computer science to general simplicial complexes, and that this will allow us to prove, for instance, fast mixing theorems for fast mixing of walks on spanning trees or independent sets or other types of objects that aren't product spaces, but turns out, if viewed as a simplicial complex, sort of act independent in this type of behavior. So we're going to see that this is sort of a very powerful generalization of lots of classical tools in theoretical computer science. Maybe after the break, I'll like literally write out the hypercube as a simplicial complex to make things clear. But let's actually try to get to the definition, full definition of high-dimensional expansion. Okay, so let's say we move away from the partite case, right? This definition is nice when your hypergraph is partite, but this like xi comma xj is only well defined when I have coordinates, right? When I have a set, the marginal xi xj doesn't make any sense. It doesn't mean anything because the coordinates are not meaningful. So does anyone have a natural suggestion for how we can generalize sort of this pairwise notion of independence when we have sets instead of having partite complex? Sorry, so you're like giving every possible ordering, or? Good. So the problem with this is that the things will end up becoming very unbalanced depending on how you try to stamp it. However, if you do this by including every possible stamped ordering, this will actually work. I'm going to take a slightly different angle, but it's completely equivalent. So you can do that. Then every xi xj will become what I'm about to say. So that is a way you can go. Yeah, this would, this would, this is like a deep, very good. Yeah, I hadn't thought of this. This is like the natural decover where I put in every possible permutation of, right, before there were just two possible VW or WV. Instead, I would do by taking every possible ordering of the hyperedge. And you can indeed do the whole unordered theory exactly in this way, but I think it's a little bit cleaner to, and typically when you look at high-dimensional expansion in the literature, it's not going to be defined this way. It's going to be defined about how I'm going to say, but it'll be connected to this. So an equivalent way to doing this sort of stamping or decover procedure is to say, well, I have a set, x1 through xd. Instead of looking at it, all the pairwise marginals xi xj, which no longer makes sense because I don't have coordinates, I should look at pairwise correlations in this by picking a random edge, right? I have x1 through xd. I'll just pick two vertices from it randomly to generate, a pair VW. And hopefully people recognize this because it's exactly how we defined this distribution pi2. In other words, if I take my unordered distribution x1 through xd and I draw a random pair, the corresponding object is exactly this underlying base graph of the complex. If I draw out, this could have gone from pi3 to much higher. If I draw a random pair, it's just this sort of underlying graph that's sitting here, right? In this case, it's a complete graph on four vertices, but it might be some general object underlying. And this exactly captures pairwise correlations in the hyperedges, right? Because it's defined as a random pair picked for some hyperedge. So this is the classical definition of high-dimensional expansion, is that we first require that this underlying graph is a lambda expander, and then we require it under conditioning, just like we did under here. We said that what's sort of so powerful about product spaces or the complete complex is that even after you fix some of the variables, the rest of them still act independent. They still act nicely. So we're still going to want that over here. So here's the actual full general definition. That's called local spectral expansion. This is usually attributed to Oppenheim. The original paper was in 14. I'll mention, I won't write down all of the names, but this sort of notion of spectral high-dimensional expansion didn't arise sort of in a void. It came from a lot of earlier work in algebra and algebraic topology, studying notions of Gromov, and also these Ramanujan complexes of Blatsky, Samuels, Vishne, and a number of other people independently developed these maybe in like 2004, 2005. So there's a lot of prior history to local spectral expansion, but we'll sort of focus on this, which is more now the modern theory of high-dimensional expansion. So what's the definition? Okay, I guess I don't actually have time to define a link. So I'm going to give a slightly informal definition, and then after the break, I'll make everything fully formal. So the one skeleton, I shouldn't say one skeleton, but this underlying graph, so I'll call it the one skeleton of X, is a lambda expander. And this remains true under conditioning. This remains true even if I fix some of the values in this set, x1 through xd. Maybe it's not entirely clear what I mean by this for the moment, but I guess I'm out of time, right? So maybe I should do it after the break. I'll just say roughly what does it mean to fix, to look at a conditional thing in this complex. Say I want to fix one of the variables to be 1. I'll look at all of the hyperedges that contain 1, and then I'll remove 1. And this will get me a graph that's called the link. So basically, X and all of its links should have expanding underlying graphs. We'll formalize this after the break. So it remains true. I'll just write under conditioning. This is, exactly the same. If you did this sort of parts ID cover, this is exactly the same as, formally fixing the variables as we did over there and looking at the conditional distribution. We want all of these underlying graphs everywhere locally in the complex to be spectral expanders. Okay, and I'll formally define these local conditionings combinatorially on this object after the break, but I think I'm a bit over time for this lecture, so.